in opposite directions in the space between them. And so this would be like the wire on this side, your right, with the magnetic field going from north to south. So it would be away from you on this side or between the two wires. Well, the current over here in this wire, the one on the left, will produce a magnetic field that's away from you, farther to the left, towards you, between the two wires. So that would be like a magnet arranged like this. So these two wires are producing in the region between them a magnetic field that, from the wire that's on the right, a magnetic field that's away from you, between the two wires, while the wire that's on the left produces a magnetic field that's towards you between the two wires. And you can see that's like having two magnets with their poles opposing, so they'd want to come together, just like this. So horizontally, we got magnetic fields all the way up and down, like they're being produced by magnets like this, right where the wires are. Does that make sense? And if we have currents going in opposite directions, that'll flip. Say we have the current on the wire that's closest to me, on your right, still going down, but the current on the left side going up, that means it's going to produce a magnetic field that's going to curve counterclockwise if you look at it from above. And so it would also be producing magnetic field towards you between the two wires. So it's going to look like this. And you see when magnets are arranged with their poles aligned like that, they'll want to push each other apart. Is this making a bit more sense? I had somebody ask me about this after class on Wednesday. But this is kind of what's going on. Okay, so here we go with the parallel. See them come together. And if I switch to anti-parallel, are they going in opposite directions? Are they pushing apart? It's hard to see from where I am. Okay. Now, something that was quite evident from the electricity activities that we did on Monday is that moving charge does produce. Where's your brother? I thought he was going to be here.
Yeah, he did, so I did to bail out.
Okay. As we talked about on Monday, we know that a current moving charge will deflect a compass. And fundamentally, that's where all magnetic field comes from. It comes from moving electric charges. And in the activity, we could tell that the current had a direction, but we couldn't tell which way. And that it clearly, when the wires are arranged one way, it caused the compass needle to go clockwise, and going the other way, it caused the needle on the compass to go counterclockwise. So there's clearly some directionality, but there's nothing we can do to determine that direction. And that was pretty much the case all the way up until the mid-1800s. And it wasn't until the later part of that century that folks started to see some, have some experiments where they could start to get a clue. And one of them was the cathode ray tube. And what I have here, I'll just, don't turn all the lights off just yet. Basically, long before we developed the technology to do these, people hypothesized that, well, we know that the magnetic field will produce a force on a current carried wire. This was something that was observed not very long after Oersted made his first observation that there was in fact a connection. Because again, prior to the 1820s, nobody even had a clue that there was a link between electricity and magnetism. And all of Ben Franklin's experiments were done, 50 to 60 years before this. Actually 70 to 50 years before this. But he had no idea that magnetism might be involved. And it was hypothesized that if we could actually get the charge carrier moving where we could observe it, we might be able to observe a deflection or a force on a wire from a magnetic field, kind of like what we saw here. But until you actually knew what the charge carriers were, you couldn't predict, is it negative charge moving one way or positive charge moving the opposite direction? We really couldn't tell from experiments even like this, where I had the parallel and anti-parallel currents. But, and this actually drove the development of the cathode ray tube. In that if we could, the idea that whatever is carrying the electricity in a material are charges that can move freely over long distances in a metal. That means that their binding to any one particular atom or location is less. And so it's hypothesized that if we had enough energy, we could actually liberate these charge carriers from the metal. And if we could observe them moving outside the metal, we could then determine what charge they were by seeing their interaction with the magnetic field. And that's essentially what we're doing here. What I have here is a cathode ray tube where we get basically an electron beam. And I thought you guys said you had this.
I had it working.
Okay, let me just fiddle this up.
There we go.
Okay, we'll turn these lights off for this. So you should see a faint green beam going from your left to your right. Is that showing up on the camera okay? What's happening is we have electrons being emitted from what we call a cathode over here. And there's a voltage across this tube so that they're going to be accelerated to your right. And they have to pass through a thin slit over here so that we get a beam. You're not actually seeing electrons. What you're seeing is basically a metal plate that's being struck by these electrons. And the metal plate has a phosphor chemical on it that basically glows for a little bit after it's struck by an electric charge. So you're not seeing the beam itself, you're seeing where the beam has struck a piece of metal that's got a phosphor chemical on it that glows. So you can see where the electrons were. Does that make sense? You can't actually see electrons. But if I bring a magnet nearby, you should see a deflection. I can't tell, is this being pushed up or down? It's being pushed up, pulled up? Well, if I turn the magnet around, now what's happening? Is it going down?
Yeah, it's reflecting downward a wall.
Okay, downwards, we're here, upwards. Again, I can't see it. Okay, lights, please. And so doing experiments like this, actually the first ones they did, they actually applied heat to what we call the cathode, or the negative terminal. Actually, they did it to pretty much, what they did is they heated a chunk of metal in the middle first, and then they applied a voltage or electric field going one way, and they were going to see then if whatever is emitted would go to the right or to the left. So that's the first experiments. But once they did and used this, we could verify, in fact, that's the negative charge that is the charge carrier. And even when they first did this, we had no idea what electrons were. We didn't know the nature of this particle. And it took a lot of more investigative work to determine that the electron was a fundamental part of the atom. And we talked a little bit about that earlier in this semester. We'll talk more about it later. But this was the first clue. And what you saw here is called the Lorentz force. The idea that a moving electric charge will experience a force if it moves through a magnetic field. And the way this is done is, well, the force basically, the force is equal to the product of the charge in coulombs, the velocity, and the magnetic field. So you multiply those three together, that gives you the force. but the direction is very important. We again use what's called the right-hand rule. And I'm not going to write this on the board, I'm going to describe it. If you stick your hand in the direction of motion of the charge, and you curl the fingers of your right hand to point in the direction of the magnetic field, your thumb will point in the direction of the force. So this force is perpendicular to both the magnetic field and the velocity. So in this case, the charge has had a velocity in this direction, off to your right. The magnetic field from the bar magnet was either towards you or away from you. So velocity in this direction, magnetic field either this way, right towards you, or right away from you. That meant the magnetic force on the charge was either up or down, perpendicular to both the velocity and the magnetic field. And so again, you stick your hand in the direction of velocity, curl your fingers to the point in the magnetic field, and your thumb will point in the direction of the force on a positive charge. If you change the sign of Q so it's negative, well, that flips the direction of the force. Basically, the force on a positive charge will be one direction from the same magnetic field, if it's moving the same direction as a negative charge, but because the negative charge has an opposite sign for its charge, the force is opposite. So you'll have the force on a negative charge in the exact opposite direction as the force on a positive charge. And it's this fact that told us whether or not we're dealing with positive charges carrying electricity or negative charges carrying electricity. And it was actually confirmed initially through looking at the force on charges and the voltage that you could see across a strip carrying a metal strip carrying current through something called the Hall effect. But we're not going to get into that, but it's essentially the same effect. That basically the force on a moving charge is going to be perpendicular to its motion and perpendicular to the magnetic field. And seeing which way that force is tells us whether or not it's a negative charge or a positive charge. Because up to this point, we could have had positive charges moving in this direction carrying the current, or negative charges moving in this direction carrying the current. Experiments like this, or the compass experiments we did on Monday, couldn't discern those two possibilities. It took something like this for us to learn what was going on. And that didn't happen until, well, that was less than 200 years ago. So pretty recent. Yeah, in fact, quite recent, like more like 170 years ago. So not within any of our lifetimes, but my great-grandparents were around. So there's that. But one thing that was going on as soon as Oersted made his observation, and this is actually kind of momentous in history, in that Oersted showed that you can get a magnetic field from electricity. Almost immediately, people were saying, well, what if there's some symmetry? What if we can somehow use magnetic fields to make electricity? And this was viewed by many almost immediately as being very, very intriguing, because electricity was very, very useful. Not only did it make a lot of people a lot of money in these electric houses, which I referred to, but probably shouldn't dwell on. There's a lot of cool things folks knew that you could do with electricity. Showed you just a few earlier this week. But the only way they could make electricity back then, in the early 1800s, was through batteries that were fairly dangerous. Lots of acid, lots of heavy metals. They were fairly toxic. they tended to catch fire and explode. They don't do that now, do they? Well, they were even worse back then. A lot more dangerous, but also very, very expensive. Batteries are incredibly cheap now compared to what they were 200 years ago. The only other option were what were called Leyden jars, basically big capacitors, like what Ben Franklin played around when he was cooking turkeys. He almost killed himself using those things. They're quite dangerous. Batteries were much safer than Leyden jars, but still pretty dangerous. And so folks immediately looked upon ways of finding a way to create electricity using magnetic field. And now I'd like to switch to that slide, if I could, please.
So it's actually creating voltage, right? A difference in electric charge?
Sorry?
Isn't what they're actually creating voltage a difference in electric charge?
Well, voltage is basically like a push. If there's a voltage present, that will cause charge to move if it can.
And that movement is what?
Is what we call electricity.
Yeah.
So you can get something to move by applying a voltage, basically applying electric field. It's just a different way of saying the same thing.
Mhm.
So here's a question. We've got a coil of iron with wire wrapped around it. Sorry, not a coil of iron. A chunk of iron with a coil of wire wrapped around it, dang it. And iron is very easily magnetized. And the question is, if we make a current flow in the wire, which of these statements is correct? Will the iron become a magnet? Or B, if the iron is a magnet, current will be made to flow in the wire? Or both of these true, both of these are true, or both are false? So there's two statements here really to focus on. The current will make the iron a magnet, or a magnet will make current. Two statements. Are they both correct or both false? So there's really all possibilities here. So if you answer A, that means A and only A is correct. If you answer B, that means B and only B is correct. And if you answer C, both A and B are correct. And if you answer D, neither A or B are correct. So that covers all logical possibilities. So think about this for a bit, please. Okay, go ahead and show me your cards. That should be enough time. What's it look like on chat?
5 C's so far, and that's it.
6 C's.
6 C's.
7. Unanimously, Charlie.
Okay, so looking at everybody then, we've got folks choosing A, B, or C. Nobody's choosing D. I'm going to go ahead and say that D is not correct. It's either A, B, or C. Let's go in reverse order. Can someone explain why C is correct? If you're remote, go ahead and unmute and speak up. Anybody here in class want to defend C? Sir, Mr.
Horsley?
Horsley. Oh,
So,
I've got stuff for you.
awesome. So my guess is, I remember the lab where we had the wrapped wire around, I think, a bolt, and when we put electricity through it, it became a magnet. And then I think they have, well, for the magnet with the coil around it, it's kind of like how alternators work in the car, I think. And when you spin the magnet, it creates a current, I think. So,
Okay, so basically B describes how we make electricity in a alternator. That's what you're saying. Okay. And how about A?
oh, just back to that little experiment we did with wire coiled around a knot.
Okay, so just what with the electromagnet we had in class.
Mhm.
Okay, can I get a volunteer to defend B, that B and only B is correct. Did everybody remote hear Mr. Horsley's explanation? Basically that C is correct because A is like an electromagnet and B is like an alternator. What generates electricity in a car? It's basically what we call a generator. And Mr. Horsley, could you describe how that works again?
So in my mind, it's like I think it's a spinning magnet with coils of wire around it, and when that magnet is spun, it creates electricity.
Okay, so the moving magnet creates electricity in the wires. Okay, anyone to defend B and only B? Anyone? Okay, how about A? Can I get a volunteer to defend that A is correct and only A? Ma'am?
Well, I just gotta say that I know that current flow will make the iron a magnet, but I don't think the magnet can make the flow of current in the wire.
Okay, Ms. Obana?
Yes.
Okay, so A is correct in that we know we can make electromagnets, but you don't think that just a chunk of a magnet just sitting there in a coil with no motion could possibly create electricity. Okay. Did anyone want to add anything to those defenses? Could somebody speak up to defend just B? Anyone? Anyone else have anything to add to this? Okay, so it looks like it boils down to, it seems like everybody's in agreement, at least spoke up, that A is correct. The question is B also correct? What is necessary for a magnet to produce electricity? Can it just be stationary like this inside a coil, or does there have to be motion going on? Let's have some discussion.
I think they'd have to be emotional magnet.
That's what I was thinking too, because I know that there are some generators that basically use a turning magnet to generate electricity, but I don't think it works with just a static piece of metal.
So it could be that might be what I'm leaning
Yeah,
towards, 'cause it's just a static piece of metal. That's my opinion.
So I think we can kind of agree that while this reason it could be used to generate electricity, it requires some work done on it.
Dr. Steve, we got some discussion on chat if you want.
Please.
To do that. There has to be motion, and Corin Brunger agreed with Ty Case that there has to be motion, so therefore only A is correct.
Okay, we've heard some defenses, some discussion. Go ahead and show me your cards or hit that letter in chat. What's it look like online?
C's and A's, more A's than C's.
Okay, that's actually standard. We only had a few people choose A the first time around. A is the correct answer for pretty much the exact reason that Ms. Obana stated. You have to have motion between the wire and the magnet. One way to think about this historically is the Greeks looked for that kind of behavior that you'd see in B. For centuries, several thousand years ago, they saw absolutely no interaction between electric charges and things that were magnetic. But in order to see this, what we call induction, you actually have to have either a lot of charge moving or you have to have very strong magnets. We actually didn't have those available until the last few hundred years. And so really what Ørsted was able to observe really wouldn't have been very observable anytime previously in history. So basically, if B were correct, it's quite possible that even the Greeks might have noticed. But that certainly was tried. In fact, you had people making some of the largest permanent magnets that they could in an attempt to get a stronger and stronger magnetic field to create electricity in wires that they would have nearby. And they would try, they figured out fairly quickly that the coiling was important. And so they would do exactly this, have huge magnets with big coils, even more coils, stronger magnets, having the coils oriented in different ways to the magnetic field. And they couldn't see anything until a guy by the name of Lorentz said, what was it, Faraday? No, it was Lorentz that basically observed that you could move the magnet, move the magnet and get electricity. And Faraday then explained that if we move the coil of wire, we get the same effect. It was one or the other. I sometimes get it mixed up. So, a strong magnet near a coil of wire is just not going to produce electricity. But if we talk about the, oh dang, I'm done.
Here's on the far left.
Actually, I think it works better if it's over here. Yeah. Dang. We need better leads. Braden, these keep cutting off. As I even move them a little bit, they come off. So yeah, if you can hold that. So if we, as Lorentz was saying, a moving charge in a magnetic field will give us deflection, kind of like we saw in the electron beam. So inside this metal, there are charges that can move, electrons that are free to move around. And if we force them to move past a magnet, they're going to get a push on them. It's going to be to the side. So the magnetic field for the bar magnet, loops around like this. So in the coil, the magnetic field is going to be coming out like this or going down like this. So basically, magnetic field is going to be kind of in this direction, outwards. And if we move the coil in this direction, the force on the wire is going to be perpendicular to this motion and perpendicular to the magnetic field, which is going out. That means the force on the charges in the wire are going to be along the wires. And that will push either the charge clockwise or counterclockwise through these loops. And you see that? We get electric current by moving the metal past the magnet. And as Faraday then asserted, if we change the magnetic field in a stationary loop of wire, changing the magnetic field, or what he called the flux, that will create a voltage or an EMF or a force on the charge carriers. So if I move the magnet, we get the same result. By moving the magnet, I'm making the magnetic field stronger than weaker inside the coil. And that results in electricity as well. So you either have to move metal past a magnet or a magnet past metal. Either make the magnetic field change its strength near something that electric charge, is free to move, and that will cause that electric charge to move, or you force the electric charge to move near a magnet, and it's going to get pushed to one side or the other. Those are two ways of explaining what was being observed. And you kind of think that the two might just be the same sort of phenomena involving relative motion, maybe? Does that make sense? Yes. In fact, a fellow by the name of Einstein was the first one to take this very, very seriously. That all that mattered is relative changes in electric and magnetic field. That's all that's required. All that's required is relative motion between the coil of wire and the magnet. The only problem with that is that by saying that it's essentially the same phenomena, that implied that there was no preferred reference frame if all that mattered was relative motion. And while a lot of people said, oh yeah, this is probably just the same thing, it's, oh, wait, no, wait. That would mean there wouldn't be a preferred reference frame. And the problem is if you once you went down that road, that it didn't matter whether or not the electric field was changing and the magnetic field was changing, all that mattered is the relative change between them. That opened up some rather sticky cans of worms. And let me illustrate that with just an example. Like with the parallel wires, if we had two electric charges, say, heading up the aisle real fast, two positive charges. Well, because of the parallel current that essentially is involved in moving charges, there would be an attraction between them, a slight magnetic attraction, right? Because it's like two parallel wires. But because they have the same electric charge, they would also should be repelled from each other. So if we're observing two charges zinging down that way, we would see them start to split apart. But we would see a force on them slightly less than what we would expect if we just had considered the electric interaction between them. But however, if you were camped out on a lawn chair on one of these electric charges, it's not moving in your reference frame. The only force you see is the electric repulsion from the other charge. You would see a different acceleration of that charge away from you than you would if you were in this room watching the two charges zing down the aisle. You would disagree on the forces that are present. Yet you would observe the same phenomena. You could even set up markers to see, how long would it take for them to be like 10 centimeters apart versus 20 centimeters apart versus 30 centimeters apart. You would observe the same phenomena, but since you observe different accelerations, you would claim those occurrences happened at different times. You would disagree with a different observer on the passage of time. And also on the distance they traveled in any time interval as a result. So saying that all that matters is relative change in electric and magnetic fields, but it doesn't matter which coil, whether we move the coil or the magnet, by saying that's the same thing, that's equivalently saying that our perception of time and space is dependent on our reference frame. And of course, that was ludicrous. Oh, that can't possibly be true. And so it was dismissed right out. That little problem was, people were quite aware of it for over 50 years before Einstein came on the scene. In fact, Maxwell, James Clerk Maxwell, a brilliant physicist, unified what we call the theories of electricity and magnetism, arguing that a changing electric field will create a magnetic field. And therefore, a changing magnetic field will create an electric field. And he even worked out the mathematics to show that mathematically, the Lorentz force and Faraday's law of induction were mathematically equivalent to each other. So basically kind of, in a way, beating Einstein to the punch, but he didn't delve into the whole reference frame problem. But he did predict that, in fact, there would be electric and magnetic disturbances resulting from any time you had sudden motion of electric charges or sudden changes in magnetic field. And in fact, he solved those equations to show that what would happen would be a changing magnetic field creates a changing electric field, which would then propagate outward, creating a changing magnetic field, which in turn would create a changing electric field, and vice versa. And this disturbance would propagate, and he actually calculated what the speed of that disturbance would be. And it turned out to be identical to the measured speed of light. He then conjectured that light itself can be viewed as an electromagnetic phenomena, that light is essentially electromagnetic waves. And he predicted a lot of phenomena that could be immediately tested and observed. The most prominent of which was radio. He hypothesized that if we set up strong electrical currents in a large conductor, that would create a disturbance that could be detected in distant places and even be used for communication. Within 1 year of Maxwell proposing this, the Marconi brothers were exchanging radio transmissions across the Atlantic Ocean. This was incredible. Maxwell gave us radio. And in fact, folks were, quite complimentary. Great job, Max, you gave us radio, but we know your theory's wrong, because it would imply that there is no preferred reference frame. And he would mean, I'm sorry, Max, that was good. There's got to be something about your theory that's right. But, overall, it's garbage, because, we know that different people in different reference frames are not going to see a different passage of time, and we're not going to see different measurements of displacement and distance, based on, the reference frame and their motion. It's just impossible. And Maxwell committed suicide. Not because of this, it was over a woman. Had nothing to do with criticism of his theories. But it was tragic that he died at a fairly young age because of relationship trouble. Okay, so a little bit of history, but this is frankly profound. So much of our technology is based on electromagnetism. And what you saw here is the first clue that maybe things are a bit more complicated than even folks thought at the turn of the century. It turns out that Einstein was right in that there is reference frame dependence for both time and space. And Maxwell is completely vindicated now. So that was pretty darn cool. But this showed us how to create electricity. All we need to do is move metal past a magnet or a magnet past metal. And it frankly doesn't matter which we do. Most of the time, we move coils of wire past magnets because they are typically lighter and easier to move around than strong magnets. That's no longer quite the case now that we have some very strong permanent magnets. Neodymium iron boride, to be specific. These are iron ceramics. The strongest inexpensive magnets we have. And we first started to develop these about 30 years ago. At least, okay, not actually longer than that. But their manufacture really dropped in price about 30 years ago, and they started to become common. When I was your age, if we wanted headphones, they had to be these big, massive creatures that were actually quite heavy. Because in order to have a good speaker, you had to have a very strong magnet. And the ceramic magnets back then, to get a stronger magnet, they had to be bigger and heavier.
You had a question.
We do?
Yeah,
What's the question?
What are they called? I'm assuming in reference to the magnets.
These guys?
Yeah.
The material is neodymium iron boride. It's an iron ceramic. They're like almost 90% iron and a fraction of a percent of neodymium. Yeah, we call them neodymium iron boride. So you got boron in them, iron in them, and neodymium in a rather complicated structure. So they're mostly iron, but they've got neodymium and boron in them. And they're manufactured rather, well, the process is not simple, but they're very, very strong. And we can make now magnets that are incredibly strong, very, very tiny. So now you can have teeny, teeny speakers that can fit inside your ear because we can make much smaller, very strong magnets. We can make microphones that are really, really teeny now for that same reason. But when I was your age, they had to be really, really big and massive. And we had to have speakers that were like in cabinets, big, huge boxes. We couldn't make them any smaller because they had to have large magnets in them. Does anybody still have one of the big speakers in a big box? Anybody still have any of those? They're becoming more rare.
I think we have some old radios in my house that use something like that. They're like yay big, yay wide.
Yeah. Okay, but anyway, one thing I can illustrate with magnets, these are very, very strong. And they can attract even through my hand. And I mentioned this before, but we are transparent to static magnetic field. Magnetic field has absolutely no effect on human physiology or tissue as long as it's not changing at high rates at time. And when it does change, when you have a rapidly changing magnetic field, it pretty much only affects the the nucleus of the atoms that comprise your body. That does not affect any sort of chemistry in your body. So that also does not create any physiological effects, but you can use it for imaging. This is where magnetic resonance imaging comes from, or what it used to be called nuclear magnetic resonance imaging, NMRs, in that it's the resonance of the nuclei of the atoms in your body. They typically look at hydrogen and look for its resonances because that's the most common atom in your body. And different tissues have different ratios of hydrogen. And so by looking at see where the magnetism, a rapidly changing magnetic field is either is absorbed or resonates with your body, you can basically map out in your body the hydrogen concentration, which can also image organs because different organs have different amounts of, water or other materials or chemicals in them. So our most accurate imaging revolves on looking at the resonance, the magnetic resonances of the atomic nucleus in different molecules in your body. And the reason that works is, again, we're transparent to magnetic field because it has no effect on our physiology. Remember this if somebody tries to sell you an arm brace, wristband, or shoe insert or something, belts, with magnets in them, and they tell you that it's for the relief of pain. They are lying to you. They are either delusional or their lie is deliberate to try to rip you off and steal your money. Remember this. It is complete and total quackery for people to claim that magnetism can relieve pain. It does not. It's entirely what we call the placebo effect. The human brain is amazing. We can wish ourselves well. Good thoughts can heal you, bad thoughts can make you more sick. This is pretty weird, but it's not unique to humans. Other animals have this as well. The power of our brains are frankly amazing. But a lot of medical technology relies on magnetism because, again, we're transparent to it, so it's excellent for imaging. Every tissue in our body produces weak magnetic fields, but the strength of those fields are about 9 orders of magnitude weaker than the electric signals that are produced by those same tissues. Electric signals, however, are damped very, very quickly in our bodies. They do not penetrate or persist for more than a centimeter in most cases, and sometimes it's only millimeters. But magnetism goes all the way through our bodies without diminishing because it has no effect on our tissue. And for that reason, magnetic imaging is becoming more and more important in our medicine. We talked about EEGs, looking for electrical signals like in our brain. They're only sensitive to, again, to about a centimeter depth in your brain tissue. But MEGs, magnetoencephalograms, can probe the entire brain. The only problem is those signals are very hard to detect because they're so weak, but we're making incredible advances in detecting even weak magnetic fields. And so we will see EEGs fade in importance as our ability to detect and analyze magnetic signals become more and more possible. So I just thought I'd throw that out. But this whole electromagnetic interaction is very, very important. I mentioned that it has no effect on pain in our bodies. Remember, I talked about how every cell in our body is like a charged capacitor, where we have a flow of sodium ions and potassium ions across our cell membranes. This is like a wave that you see going on in a stadium. Very little charge flows, and it only flows over a very, very short distance, fraction of a micron, and it doesn't really go all that fast. So yes, moving charge will have an effect, will be affected by magnetic fields, but since the electricity that drives our cellular function is, well, ions moving very slowly over very short distances, it really has no effect. Some Russians did an experiment where they pretty much put the entire output of a very large hydroelectric dam, put all that current into some giant electromagnets around a closet and had a guy sit in there for about 6 days. The guy got very, very cranky after a while. It's not certain if he was irritable and angry because of the confinement or because of the effect of the magnetic field, but that's the only effect they could discern on the human body. on his physiology from some of the strongest magnetic fields mankind has ever produced. So the idea that we would somehow affect pain signals, nervous signals, is incredibly ludicrous. In fact, if you look at our nerve sheathing, the signals that carry pain are the most protected. In our nerve bundles, those are the most central and core nerves that carry those signals. The ones that are the least protected in our bodies, the ones that are more prone to damage, are the kinesthetic sense, your sense of where your fingers are. So if magnetism did have effect on nervous signals, the first noticeable effect would be that you would get remarkably clumsy. The absolute last sensation or communication in your body that would be affected would be that of pain. So again, there's this whole idea of magnets for pain relief is so wrong on so many levels. Okay, well, let's get back to this. We can create electricity. This is how we now generate electricity. I mentioned that this got a lot of people's attention back in the 1800s. Well, for the first time in history, because of Oersted's observation, you had nation states funding direct scientific investigations. So that for the very first time in history, you had governments funding directed scientific research to answer this question: how can you get electricity using magnets? And it only took about 20 years before we had the first remarkably efficient generators, where basically we flipped loops of wire past magnets. And I don't think we have time to play around with the generators that I have out, but I think I'll at least demonstrate them a little bit. In that, remember in a motor, we send electricity through loops of wire, and they're near magnets, and therefore the wire spun. Well, a generator is much the same thing. Instead of sending electricity into loops of wire near magnets, and then having them spin because this Lorentz force, if we spin the loops of wire near magnets, out comes electricity. So really, a motor and a generator are the same device, just used differently. In fact, this is the hand crank generators I was going to have all of you play with in class today, but I'll have to wait until Monday. This is a DC hobby motor, if you look at it. Take apart any sort of little toy car or a fan, you've got one of these guys in there. Basically, there's a bunch of coils of wire near magnets, like the demonstration motor I had out here on Wednesday. And if we turn the crank, we flip those wires past some magnets.
So basically, it's doing the opposite. Instead of converting electricity into motion, we're converting motion into electricity.
Exactly. In fact, a motor is not just the same thing as a generator. Any generator could be used as a motor. So if I hook two of these up and I use one to produce electricity and send it into the other one, you can see it's really the same thing. And there are places where it's not very economic feasible, but it's done in a few places to basically have two reservoirs, one at different elevations. And during the day, water flows from the upper reservoir down to the lower one. And that generates electricity. That basically spins big loops of wire past magnets to create electricity. And so that reservoir falls while the other one goes up. And then at night, where they've got other power sources that the demand for electricity is less, they can divert power to those turbines and instead run them as pumps to pump water back up to the upper reservoir to essentially store energy. That's not very efficient, but it's one way of dealing with the intermittent energy that you could get from, say, solar power and wind power to even things out. One setback to our energy system, because wind and energy are not reliable in that they depend on wind and sunlight, we have to have massive amounts of generators backing up any sort of power grid. So we have to still have coal, oil, and natural gas plants to fill in the gaps. In fact, those generators have to be kept running and operational all times in order to be able to step in at a moment's notice if there's a drop in the wind or in sunlight, if say a cloud or a storm front comes in. We'll talk more about this on Monday. Thank you for your attention.
basically using the potential energy in a reservoir as a giant battery, huh?
Yeah,
I got for Steve.
yes,
So here's my lab paper,
okay,
and here's the equipment,
wonderful.
and so this
Yeah.
battery hybrid, I'm not sure